right, so picking up where we left yesterday, we were talking about endergonic and exergonic reactions, releasing energy or requiring energy. So eventually, a reaction will reach equilibrium. Basically, the reaction is over. So for example, we talked about in diffusion, you would reach isotonic and the amount going in each direction would be equal. And at that point, delta G, the change in free energy, would be 0 because there wouldn't be a net change in gaining or losing energy. But in living cells, it's different. We're not the same as a closed system. A closed system is sort of you carrying out a reaction in the chemistry lab. You put the stuff in a test tube, the reaction happens, the reaction's over. Or you did the dialysis tubing, you put it in, the reaction ends. But in a living cell, we're not a closed system. We don't mix two things together and then that's it, we don't touch it. What's happening in a living cell is you're constantly taking in oxygen, taking in food products, producing waste products, moving. All kinds of reactions are always happening. So it's called an open system. And there is no 0 point of delta G because reactions are always happening. So here's an illustration. So this is a closed system. Notice no water's coming in. You start with a certain amount. The reaction has a negative delta G. Energy is being released as the water flows, and the energy is lighting the light bulb. But eventually, delta G is 0 because it reaches equilibrium. This is more like what's going on with us. It's an open system. So we're constantly taking in, notice water's coming in, waste is going out, and delta G is never 0 because the water flow is constant. And actually in our cells, it's probably more like this picture because we have what we call, I mentioned this yesterday, metabolic pathways, where one reaction, the products go to the next reaction, and the products of that go to the next reaction, and, etc. And so it's a multi-step pathway. So, moving along, cells do work, and there's 3 main kinds of work. In other words, what are the cells using energy for? Well, we have chemical work, where they're building and breaking things down, making and breaking bonds. Transport, like the sodium-potassium pump, carrying things in and out. And then mechanical work, like literal motion of the chromosomes, motion of the organelles, or even motion of the whole cell, like muscle contraction or endocytosis. So in order to do work, the cells do what's called energy coupling, meaning they capture energy from an exergonic reaction and then use that to run an endergonic reaction. So in a lab, you mix some stuff in a test tube or a beaker, the reaction happens, and maybe some energy is given off. Maybe you see a fire, you see heat, you see light, and then the reaction is over. In your cell, that would be kind of wasteful. If the delta G of this is negative, let's just say is negative 10 joules. So this actually released 10 joules of energy as heat. Your cells have some reactions that are releasing, let's just say, 10 joules of energy. But rather than just releasing it as heat, which would be kind of wasteful, there's other reactions in a cell that need 10 joules of energy to run. So what better way than to do what's called energy coupling? What the cell will actually do is take the energy that's released here, transfer it to another reaction that needs energy. Sort of like if you buy your lunch and you have some extra money and the person next to you forgot their money. They need money for lunch. You could either just throw the money away, which is sort of what's happening here, is the energy is just released. Or how about that person that needs the money, you give them the money. And now you, because you had extra, you provided something. So that's called energy coupling. And the molecule that does that for a cell is ATP. That's what ATP actually does. It's an energy carrier, and it carries energy from an exergonic reaction. It captures it and carries it over to a reaction that needs it, rather than you just releasing that energy. So most energy coupling, like I said, is mediated by ATP. So this is a picture of ATP. It is, sometimes we draw the phosphates this way, and when ATP breaks, if you recall from our previous chapter, it forms ADP, and it releases the phosphate. And that's actually where the energy comes from, is breaking off that phosphate. So ATP, it stands for adenosine triphosphate. It's ribose, which is the sugar. Technically it's a nucleic acid. So ribose is the sugar, adenine is the base, and then 3 phosphates. And that's why it is a nucleic acid. It is an energy carrier. What it does is energy coupling. It captures the energy from an exergonic reaction when that energy is released, and it brings it over to an endergonic reaction that needs it. And the way it does that is using that 3rd phosphate. when that third phosphate breaks off and attaches to something, it is called phosphorylation. And if you think about it, we saw this in the sodium-potassium pump. In the sodium-potassium pump, the 3 sodiums lined up here in the pump, and then ATP came along and dropped off a phosphate. And when that phosphate attached, that is what caused the pump to change its shape and release the sodiums, and then it could pick up the potassiums. So the phosphate of ATP, when it was given to this molecule, it changed the shape of it. And so the sodium-potassium pump will be an example of where ATP provided the energy for a reaction. So ATP, again, it becomes ADP when it breaks, that phosphate breaks off, and it releases energy when it does that, and then you rebuild it as you need it. So here's exergonic reactions that are releasing energy, and they are used to build ATP. ATP, the phosphate gets attached, and now the ATP can pass that energy on to endergonic reactions. So this reaction needs energy. This reaction released energy, and ATP carries the energy over, and then you have to rebuild it. And you do that through cell respiration, which is actually our next chapter. Now, keep in mind that ATP is not a long-term energy storage molecule. It is for short-term only. So you basically, about every second, you're making and breaking about 10 million ATP. So you don't store energy in ATP. It just literally carries energy over really quick, sort of like playing a game of hot potato. They throw it to you, you throw it to the next person. Your ATP is passing the energy along. And this is just some pictures showing it. The phosphate at the top causes the protein to change shape. At the bottom, it's actually allowing this protein to move, is what they're trying to show here. All right, now, here's the next thing. So chemical reactions always involve bonds breaking, bonds forming, and even though a reaction might be spontaneous, meaning that reaction releases energy, remember something like this. So this would be a negative delta G, and energy is being released. That doesn't mean that the reaction is going to happen fast. Just because a reaction releases energy and is spontaneous, the word spontaneous doesn't mean it happens right away. And the reason why a reaction that's spontaneous doesn't necessarily happen right away is because of something called activation energy. And it's represented with an E with a little a, or the energy of activation. Now this is really important because if there was no such thing as activation energy, then every reaction that releases energy would happen immediately. In other words, we wouldn't be alive because every reaction would happen, every reaction that could happen. So there must be something that's stopping these reactions from happening even though they release energy. Because remember, that's the second law of thermodynamics, that everything goes towards a state of entropy. So molecules should break down. Why don't they all break down? Why don't we just burst into flames? And the answer is activation energy. So activation energy, one of the reasons that a reaction might happen when you heat it up is because heat provides that kickstart, that activation energy. In the lab, a lot of times we'll heat stuff to get a reaction going. So this graph is showing activation energy. This, if we turn this back into a bar graph again, this is the amount of energy in the reactants. And here is the amount of energy in the products. So energy is released by this reaction. If all we look at is the bars, here and here, that's delta G. And it's a negative delta G. Energy is being released. But in order for the reaction to get started, it needs this kickstart. That's activation energy. And a really good example of this is peroxide, H2O2, hydrogen peroxide that you buy in the store. It breaks down into water and oxygen. This is not a balanced equation. But here's the thing. This is a spontaneous reaction. It releases energy. So then why does peroxide even exist on this planet? Because if it's a spontaneous reaction, shouldn't all the peroxide immediately break down into water? The reason it doesn't is because of activation energy. Now, if you heat peroxide, it'll make the reaction happen faster. Another thing that will speed it up is light. That's why peroxide comes in brown bottles. If I just put some peroxide in a beaker and leave it out overnight, the next day I'll see some little bubbles stuck to the side of the beaker because the peroxide has started to break down because light is providing energy, there's energy in light, to get this kick started. And once it's started, the reaction goes. Now, on the flip side of that, if I was to put a drop of blood into some peroxide, it would bubble, and within 30 seconds, all the peroxide would be broken down into water. because what we have in our body are called enzymes. And the whole job of enzymes is that enzymes are going to lower activation energy. So what enzymes do is they lower this barrier to kickstart reactions and get them started. Because we can't rely on light and heat to speed up reactions in our body. For one thing, we can't get light to the inside of our body. For another thing, heat would be damaging, and heat and light would speed up everything. Enzymes are specific. If I have 1,000 reactions in my body and I only want one of them to happen, if I add heat, they might all happen. But if I add an enzyme that only reacts with that one thing, I'm going to specifically speed up just that one reaction. Now, enzymes do not affect delta G, and I'm going to show you this in a graph. In other words, final minus initial doesn't change. But what they do is they make a reaction go faster. That reaction would normally happen slowly. Peroxide, like I said, will break down. If I put it in a beaker and leave it on my desk under some light, in a couple of days, all the peroxide will be broken down. But if I add an enzyme, I can make the peroxide break down in seconds. And here's another example. Sucrose is the sugar you buy at the store. Sucrose spontaneously breaks into glucose and fructose. This is a spontaneous reaction and has a negative delta G. But I can guarantee you that if I go into my kitchen right now and I have sucrose, sugar that I went and bought at Publix, it could be sitting in my kitchen for 10 years and it probably would not break down at all, or maybe a tiny bit, unless I heat it or I add energy somehow to get that reaction started. On the other hand, if I add sucrase, an enzyme, I can break all the sucrose down in just a matter of seconds. So enzymes speed up reactions. And we're going to wrap it up with this graph here. So this graph, guarantee you it will be on my test. And it will probably be on the AP exam too. Here's delta G here. Remember the original graph we looked at. Here's the products, here's the reactants, and delta G is just final minus initial. It doesn't matter what happens in the middle. So delta G is not affected by enzymes. Here's the activation energy that's necessary to get the reaction started. Heat would add activation energy. Light might add activation energy. But what an enzyme does is it lowers the activation energy. So the two other things that you should be able to label on this graph on a test would be activation energy without the enzyme, which is going to be from here to here, the big hump, and then activation energy when an enzyme is added, which is a lower hump. So by lowering the activation energy, an enzyme can get a reaction to go faster. It didn't change delta G. I add enzyme, I don't add enzyme, delta G is the same. I would always get to the same finish point. It's just a matter of how quickly the reaction would get there. So next time, we're going to talk about how. How does an enzyme actually do this process of lowering activation energy?